Hi, my name is Sanjeev. I am here to explain about the remotely controlled electronic throttle control. I'll rate my experience with it. At an age of 16, I have been driving my car, I have pressing my pedal and the car goes away, increasing the RPM. I don't know what the control strategy is going in my vehicle and how the engine is going well. So after coming to LHPU, I came to know that, okay, there is a control strategy within the pedal and also the throttle which is present in the car to control it. So we have done a project with the sensors and the actuators which is related to my vehicle. So this is an accelerated pedal when we compare it to a car, and here is an input of 0 to 100. So when we are at 0 stage, the accelerator is at here and the throttle accelerator doesn't allow any amount of air into the engine. So when we press the pedal, it has an accelerated pedal sensor which senses the position of the pedal and gives the signal to the electronic control module. The electronic control module takes the position from the sensor and it actuates the throttle motor which controls the butterfly spindle valve which is present on the throttle body and allows the amount of air entering into the body which is connected to the engine output and the power. So what does ECM do? ECM helps out to connect this axle pedal position and the throttle body so that the required amount of pedal position and the throttle body butterfly spindle valve opening should be done accordingly. And how we converted this pedal position to the ECM and ECM how it manages the throttle body. ECM contains an electronic sensor which has a potentiometer which also works on voltage divider. So it has a V voltage reference to the ground and also V reference. As I said, the ECM sensor reference voltage to the pedal sensor. So when you press the pedal, it alters the voltage and sends the signal back to the ECM. So the ECM collects the output voltage and sends back to the throttle to control the throttle valve. The throttle valve which is open and measures the angle and is sent back to the ECM. So ECM is the main part which helps us to understand how the pedal position and throttle actuator works. And what are the mechanisms going through it and how we are controlling the ECM with this will explain by Siddhartha.
Now we'll see how we actually developed our model. This is an instructor model and this is a student model. Our instructor has challenged us to build our own instructor model. I think we have successfully developed our instructor model. So we have a pedal position, which is an analog sensor, which represents the gas pedal in our car. So this is the potentiometer. So when we change the resistance, the voltage, effective voltage changes. So when we send the voltage, the ECU receives the voltage and it converts it into counts using a MATLAB analog input block. So we simultaneously read in the throttle sensor positions also and we convert it into counts here. So now we have the sensors information to us. So we need to send it to a controller which is at the remote location. So we have used a CAN bus to send our information. And before that we need to make sure the send CAN block here and the receive CAN block in the remote location should have the same offset and scale values to actually decode the same data. So we have used the CAN bus to send our information. So this is a controller which receives the input data. The CAN read block decodes all the data and we have given it to a PI controller which controls it, and we have given a duty cycle to the CAN bus again to give it to the ECU again here, and this ECU collects that and gives the throttle which controls it.
Sandeep and Siddhartha clearly explained why it is working and what's inside it. Now let's see how it works. As they said, this is an accelerator pedal position. When we move the accelerated pedal position, it sends the signal, as they said, and it's going to change the throttle position. And to calibrate this, we have used MotoTune, and we are sending the messages using using CANlog files, and these CANlog files can be viewed using the CANKing software.
This is the open loop control.
This is a closed loop.
Closed loop.
So you can actually see
These
how we
values
are
can-
tracking our sensor here.
You're getting back the position of that throttle.
Yeah, actually the throttle position sensors gives feedback to the ECM. So ECM makes sure the actual position and the desired position, and it calculates the error and gives back the appropriate signal to the throttle to work accordingly.
So the main control part is located at the different remote location. So the input sensor parts are calculated here. And we can look, it tracks the data here. And the red one is the APP sensor pedal position and the green one is the throttle position. So it tries to track the position.
Everyone, today we are going to talk about DTE, which is desktop environment. Once we have a model built, we need a safer environment to test our model. So we have this model built by LHB. So what basically DTE is, it is an NI hardware where it generates similar signals that has a Cummins engine inside. So that's how a desktop engine, desktop looks, and working of it will be explained by CEO.
Hi. You can see the display of an engine. Here's the RPM and here's the top. Right now the key is on. It's just the battery on position, and you can see the voltage which is above 12 volts. And I'm right now going to start the engine. You can see the RPM goes to 700, and the idle speed governor comes into the picture, and it keeps the RPM at 700 because you are not giving any APP. The APP is 0. So as you can also see the value as 700, which fluctuates sometimes between 699 and 700. So our PI controller tries to keep it at 700 for idle speed governor. So right now I'm giving my APP to 25%. You can see that our engine RPM goes to 1700, and here is the value which is going up to 1699 to 1701, and our high speed governor is trying to pull the value to 1700. So you can see that I have not given much APP, it's just 25%, so it's too sensitive. I can reduce the APP gain and make it less sensitive so that it gradually increases to 1700. I can show you that. Right now the APP gains are 1. I'll reduce it to 0.25. I'm not giving any APP right now, it's 0%. You can see the RPM coming down to 700. And now I'm giving back my APP to 25%. You can see that it's increasing slowly. It's not going rapidly, so that it achieves RPM of 1700 gradually.
Now you can see that it's running properly as we desired. But initially when we designed our model, and we designed it according to the engine specifications, but we couldn't run it here. Like, we had a few problems initially. We didn't know what is happening. Lately we figured out that the problem was it couldn't take the CAN message because this CAN message priority is different from that mesh engine priority. So this was 4 and that was 6. So later we figured it out and we could run it slowly. And figuring that out, we thought it is okay. We're going to run it and get our output. But there is another problem, and that
was the crank angle offset. So the DTE is a little more stringent. When you go onto the engine, you just have to set your cranks to a positive 120 degrees. The physical quantities on the engine, the signals are always positive, but the DTE took in a negative 120 degrees offset. The negative stands for after top dead center. So the whole demonstration highlights the fact and advantages of using a hardware in loop system. One of the advantages it has is it reduces the cost of experimentation and test equipment drastically. You can sit at a remote location and still get your plant sensors working, and you can test your embedded control system that you have implemented sitting at your desktop. One other thing is that this is a computer. It is basically robust. Consider the fact that you just didn't test on the DT and went directly onto the engine. There are concerns about safety. there are concerns about the reproducibility and precision of the engine. You might not get the same result every time because there's a lot of friction parts and there's a lot of unwanted signals in the engine. The plan model in this DT takes care of that. So it is robust, it is precise, and it also simulates safe conditions for us to test our controls on.
Hello everyone, welcome to the engine demo. I'm Kaveshri, this is Manu. We'll be just showing you everything in action. I think you guys are pretty much tired listening to so much of blabberings. So let's just get to the action. So it's just started the engine. This is my CAN. It just started communicating. Here is the engine working. So this is our. Let me just show you something in more clear. Where we have red, this is our engine speed right now, and this green line will tell us the maximum target that we have set, and the blue line will tell us the ideal speed we have set. Since I think you guys have heard that ideal speed, we are setting it at 700. So our engine is working pretty good, where it's maintaining that 700. And anyone would like to press the pedal and see how our engine is working?
You want to break this one? That's really who you want touching up the... Probably not.
Yeah, we had a calibration.
Alright, here we go. Of course, he didn't want to do what he was told to do. He's never. Your engine idle governor speed? Yeah. Nice. See?
Since we said 500 is crank.
We didn't tune it at 500, did we?
Yeah, we said like, but only the run activates after 600 because till 600 it's crank.
Fast response. Yeah. Alright.
See the pedal?
Does your high idle governor work?
Yeah.
Well, you're going to find out. Not bad.
So it's where our maximum governor is in action.
See where all you tuned it. Ooh. Impressed. Not bad. Nice. Should go. Very nice.
I think this will be looking pretty simple, but this was not our journey for the 6 weeks. We did overcome few of the problems.
We all know what it takes to actually make this happen.
Right, and one of the key takeaways that we had was trying to find the problem, because it just stops and we're sitting here and we have to go through the wires, and I think the first step is that we was trying to identify if it's an electrical problem or a mechanical problem, so that way we can sort of have a starting point. And then we did do that, and we found out that we blew a couple of fuses, which
I
we then
have
replaced.
everything on this. You can see the display, we have all the data here.
I think they're going for 5 mechanical failures per session. Working on there.
We have the record so far, so
At least we didn't do the same thing over and over again, because we had some
Different
documentation.
problems.
yeah, different problems each time.
So you're bumping in and out of something there.
There's some delay in the system because we are controlling
Changing it.
using this.
So that's did you change
Oh,
the
okay.
gains?
Yeah, this is so that we get this is our idle we are setting so that our transition is smoother.
Yeah, I understand.
Just
I'm wondering why, but this so it settles out after a while.
It's got a little bit of oscillation there.
Yeah.
And also since there's some delay between the system, it's taking some time to
You
adjust.
say that first. You change the gain.
700 is your minimum. Okay. So you don't let it go below.
on FPC, you'll see it. That won't tell you anything. Just tell you that it's doing. You can see that it's doing it. It's going like that. It'll go. It is sorting itself out. That's weird.
It's kind of weird.
Cool. Good job. What do you think? Very good. You enjoy this?
Yes,
We
we
loved
did
it.
enjoy. We learned a lot. I mean, more than learning from the requirements given to us, we learned more from the problems we face.
A lot of running around, doing that.
Yeah. So initially, for us, the system requirement was given, the software requirement, and then we were given a hardware. We were supposed to do the reverse engineering and learn.
Yep.
So we were like completely blank. What is it? I mean, I had never seen an engine, diesel engine.
Yep.
But then we got to learn a lot in these 6 weeks.
That's great. Difference between learning and experience, right?
Yeah,
Absolutely.
exactly.
Bunch of failures.
Get your hands dirty.
That's right.